Okay, let's develop a model for the behavior of a gas. We'll start here. And this is a little bit of a follow-up to the van der Waals discussion we were just having. The an idealized model of a gas is, point particles, infinitely small, that exert force on the walls of the container, but not on each other. An actual, more realistic model needs to include the interactions that those molecules have with each other. But for our purposes here, we'll stick with the ideal version. Our model makes 4 assumptions. One, we have a container of volume V containing capital N molecules. They are identical, we can't tell the difference. Each has a mass m. So m in this case is not the mass of the sample, it's the mass of the molecule. Two, these molecules are points that collide elastically with the walls but not with each other. They're so small that there's no possible way for one of them to hit the other. If it's going to hit the wall, like there's no way for it to miss, right? It's going to hit the wall. But if 2 molecules are coming at each other, they're so small, they never see each other except, I guess, maybe to like bounce off. But like they don't even know that it happened. It feels like hitting a wall. There's no difference to them. 3, and that sort of follows up, the molecules do not interact. One going by the other, they don't see each other. They have no idea that the other molecules are even there. We assume that they're very, very, very far apart compared to how big they are, which I guess that's okay because they're points, so they have no size. If there's any separation between them at all, yeah, that there's no intermolecular interactions apart maybe from an elastic collision, just 2 marbles hitting each other, no extra forces, no gravity, nothing like that. We assume that the walls are rigid, infinitely massive, and don't move. These molecules can hit the walls all day long, nothing happens, no energy. It's an elastic collision, so the energy that we have is the energy that we have. But the walls have infinite mass, so whatever energy, and don't move, so whatever energy we've got needs to stay in the box. The molecules keep the energy they have, in other words. If we make these assumptions, now, assumption number 1, That's not so. That's not so difficult. I mean, there needs to exist a container. It has a volume. Um, there need to be some molecules, and I guess yeah, sure. I mean, it makes sense for each one to have mass m. I these two assumptions kind of go together for me, um, and the elastic part of the collision goes with this one. The molecules are super 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 small compared to the space that they're in. So when one collides with a wall, I mean, it's like it's like throwing a paperclip at the actual wall. Nothing happens to the wall. The paperclip just bounces off. Rigid, infinitely massive, and don't move. If we throw a paperclip at the wall or a ping pong ball or something, even if you're on the other side of the wall, you can still hear that. But for this, we're saying no. These molecules that we're talking about are so small that nothing about their collisions with the walls makes it out of the room. And it makes no sound. There's no, friction. It's just the energy of that molecule stays in the box, which I think is reasonable. I mean, gas molecules are small, right? And this part about them not interacting, that just seems like the simplest place to start the model, right? I mean, if we allow for them to interact, then there's another term. We got to do van der Waals stuff, and we have to, the I don't know how it's going to go, but it's going to be more complicated than whatever it is we're about to do. So like, I'm not saying we couldn't do it if we needed a more precise model or a less assumptive model, but for now, for like a first try, I think this is reasonable. If the molecules don't interact, then there is no potential energy between them. If there were, then we could take a gradient of that and they would exert forces on each other. So if there aren't any forces, then there can't be a potential energy function, which means we're only talking kinetic energy. And that's the reason for the name of this model. It's the kinetic theory. In a minute, I'll switch back and stop sharing the screen so that this is legible. And before I erase it, I'll do that. Okay. The gas is going to exert pressure on the container, on the inner walls of the container. And the only way for a molecule that doesn't interact through any ranged forces, in other words, through no potential energy, nothing like that, the only way for a point particle, a point object, to interact with the wall is to hit it. That's the only thing it can do. So what we're talking about is molecular collisions with the walls. Okay. Now, molecules have, a molecule has a speed. For now, okay, fine. A molecule has a speed, and it's traveling in, some dimension, some direction, and there's some x, some y, some z components. I don't know. In the plane section that we're looking at, there's some x and some y component. The force from the wall is what changes the direction of the particle, but the walls only exert forces that are perpendicular to themselves. So there's no possible way for the vertical component to change. It can't, because the wall can't exert any forces that way. Whatever the vertical component is, the vertical component has to stay that, and that's the reason for Vy and Vy. So horizontally in the x direction. In order to keep the energy that we have, our speed needs to be the same before and after the collision, because there's no potential energy to worry about, and we can't throw any energy through the wall. It's got to stay here with this molecule. We've said that the vertical component is already the same. The speed needs to be the same, the hypotenuse here, which means the other leg also needs to be the same, just change direction. So the molecule was going to the left with some speed v sub x. Now it's going to the right with the same speed v sub x. We only changed the direction. Okay. So the momentum change, the delta p during, from one side to the other of a collision, would be momentum final minus momentum initial equals the only delta is in the x direction, so the final in the x, m vx going one way minus m vx, but this one was negative to begin with because it was going to the left. It was going to the left, now it's going to the right, to m vx. Okay. So that's one molecule. But there are capital N of them in our container. So together they all hit the wall every so often and exert so much force on the wall altogether. Let's figure out what that looks like. I've got one more slide to show us, and then I'll turn the screen sharing off. Let's talk about a small amount of time dt. The molecules that are able to hit the wall during a small amount of time dt need to have lived somewhere within a close enough distance so that they could hit the wall during that much time, according to how fast they're going. And for now, let's just, let's make one more assumption for now. We'll walk it back in a second, that every molecule has the same speed, just to keep things nice, at least, while we're working through this. So let's assume that every molecule has the same speed and dt is so and so long. In some amount of time dt, these molecules could travel a distance of v sub x, the speed, times dt. Okay. If they're going to hit the wall during time dt, that means they need to have been close enough to do that. So the farthest away that one could be is that distance that it could travel in the time interval dt. The farthest away that a molecule could be and still hit the wall during time dt is this far, vx dt. So we are interested in an area's worth of distance into the room, into the container. Why area? Because we were talking about pressure. We were talking about things hitting the wall. We care about the area. Okay. So the volume of this cylinder, because the what I'm trying to get at is how many molecules are hitting the wall every time, every time dt. How much force do they exert altogether? Over what area gets us the pressure? All right. So in any case, the volume in which the molecules need to live in order to hit the wall during time dt is a cylinder of area A and height equal to the distance that the molecules could travel in time dt, which is just Vx dt. Okay, let's pause there. And then, and stop screen sharing. I'll just give you a minute to check out the board. I just wrote down those 4 assumptions that we were going to make, and wrote down the a little bit of algebra for the momentum change of an individual molecule. Okay. The first assumption, that the container has a volume V and it contains capital N molecules. That's going to be useful for us here because there's no reason the molecules should clump any particular place. The molecular density, the population density, I suppose, should be uniform throughout. There's absolutely no reason for them to clump anywhere. We're assuming, I guess, additionally, that they're moving fast enough and are small enough that, in the time that they take to move around, gravity doesn't really get to make any difference. Up is down, is left is right. There's absolutely no reason for a molecule to prefer to be anywhere, so they should spread evenly throughout. The average molecular density, I guess, is N molecules per a volume V on average. All right. Okay. Now, how much force is exerted by one molecule on the wall? Well, it's we know from our work with Newton's second law that the force exerted by the molecule should be the change in its momentum, which we know 2mvx per time. Now, how many are there? Well, because that's one molecule. There are actually a bunch of them, right? So there are, all right, hear me out. If I know the mass density of a thing, mass per volume, if you tell me how much volume you have, I can tell you how much mass there is, right? Like if you tell me that the volume you cut a thing in half, now because of the density, I can tell you what the mass is. So finding the mass is like taking the density and multiplying by the volume. Or it's like taking the mass per volume and multiplying by the volume that we have. Whatever volume it is that we're talking about, it's what fraction of that out of the original volume? This is all to say the average molecular density is capital N per V, but we're considering a volume equal to the volume of that cylinder in the slide we were just looking at, which had an area A and a height dx dt. So this is the number per volume, and this is a volume. So this is going to get us the number of molecules that live in this volume on average. Now, on average, half of them are going one way and half of them are going the other way. So the half that are actually going to hit the wall are a half of this. And this is how many molecules there are that are going to hit the wall. This is the force that each one exerts. So the total force that is exerted on the wall, the twos cancel. Oh gosh. We've got Vx squared, whoops, the dt's cancel, that's nice. N A Vx squared over V. Oh, times N. The force exerted on that wall divided by the area of the wall is the pressure that's exerted on the wall. So we'll divide by the area, N M Vx squared over V. And we've got a relationship for the macroscopic pressure as a result of molecular properties. Because capital N and V are macroscopic as well. So, and they're set by the, assumptions we made. So we change the mass of each molecule, we change the speed, we know what the pressure is, which is pretty cool. Although we made an assumption that the speed of every molecule is the same, that they all have the same speed, Vx, in that direction when they're hitting the wall. That's not, it's not a great assumption. We should probably account for the fact that that they might have different speeds. In other words, the equality of speed was not part of the original 4 assumptions, so we should probably walk that one back. Generally speaking, each molecule has an x, a y, and a z component of its velocity. If we ask for the magnitude of the velocity squared should be the sum of the squares of the components. And here's the tricky part. We said that these molecules are so small and that they are moving so fast and in a container so small compared to the length they would have to fall for gravity to appreciably change their speeds. X is Y is Z. Take the room and rotate it. The molecules can't tell any difference. Take the room and turn it upside down. The molecules can't tell any difference. The molecules are what they are. So what we call X, what we call Y, what we call Z, I mean, it's all like it's all the same. It's just a component. The molecules don't care whether it's X or Y. They are different, but they don't care which is which. We could switch them, X and Y, with 0 cost. And frankly, we could switch, call them all Z. Who cares? Who gives a shit, right? If they're all the same, we might as well call them all the same thing. I'm just going to write Vx because that's what we've got down here. It doesn't matter, V component, whichever component it is we're talking about. So 3V component squared. So far, we haven't said anything about the fact that the speeds are different until now. The square component speed is V over 3 is a third of the square actual speed. In other words, the speed along any of the three components is just a third of the total square speed. And let's take an average. Let's just, on the average square component speed is the average square speed divided by 3. We've got speed divided, square speed divided into x, y, and z. Each component has a third of the total square speed. All right. On average, the molecules might have different speeds. So let's take an average of the square component speed. And we're going to end up taking an average of the actual total square speed and dividing that by 3 because we've got three directions. We can't tell the difference. Put that together, this x component that we're talking about here, well, there's not only one speed, there's an average, and the average square component speed is a third of the average square speed. The average square molecular speed That's pretty cool. That is a neat conclusion. That is a neat conclusion. Now, this on its own isn't quite enough for us to really justify talking about the kinetic theory as a cool thing. The rest of the story comes from here, that PV we know what that's equal to. If we express the ideal gas law in terms of the number of molecules instead of the number of moles, we said, like 15 minutes ago, that the pressure times the volume should be the molecules times Boltzmann's constant times the temperature. Again, the over bar here, this isn't a vector arrow, it's average. The number of molecules shows up on both sides, so we can cancel that. And, oh wow, the temperature, 1/3 divided by KB and we got mv squared average. Apparently, when we're talking about the temperature, we're really talking about the average square speed and the mass of the molecule. Wait. mv squared, that's like kinetic energy. Gosh, why didn't I see that before? mv squared is a kinetic energy, or it's like half a kinetic energy. So k is 1/2 mv squared. So 2k is mv squared. So we can just 1/3kb 2k average. Each one has mass m, but this is the average square speed. So we average this side, so we're averaging this side. It's the average kinetic energy. The average molecular kinetic energy. Whoa. In chapter 17, when we said temperature was hotness or coldness, okay, what is it really? And remember, this transition is from experiment. The ideal gas law is an analysis and the result of actual experiment where we show that the pressure and volume are inversely proportional to each other, that the pressure and volume are both directly proportional to the temperature. That's experimental. That's not some, conclusion that we, lucked into from the model. That's for real. So this is, that's what is temperature? When we say temperature, we must mean average molecular kinetic energy. Wow. That's so cool. And that's the 4 state variables. The number of molecules and the volume, we're given those things. That's fine. Pressure and temperature in terms of the molecular properties. We could do the same trick here with kinetic energy. Plug in 2/3 bar average. Molecular kinetic energy. Average molecular kinetic energy. Wow. That's super cool. Okay. Let's run with that a little bit. The average, 3/2kb times the temperature is going to be the average molecular kinetic energy. If we wanted to talk about the total kinetic energy of all of the capital N molecules, we'd have to multiply both sides by N. The average kinetic energy per molecule times the number of molecules is actually going to get us the total kinetic energy of this gas. And that's 3/2 N K ultimate temperature. In our kinetic theory, we assumed that the energy of the gas is entirely kinetic, that there are no potential energy interactions. So the energy that this gas has is entirely as a result of its kinetic energy. Because it's at a temperature. So change the temperature, we change the total energy content of the gas. Now, sure, if we take the container and throw it, Now there's some sort of macroscopic kinetic energy of the object entire, right? But the gas itself has an energy associated with being at a temperature. That's this whole kinetic theory thing. That's our conclusion. That's where we ended up. That this is not throwing the container. It's not it's not external energy that we came along and kicked it. It's energy by virtue of being a gas at a temperature. It's intrinsic to being a gas at a temperature. So we could call it I guess, the internal energy. Internal energy of the gas. We're going to use the letter U going forward in the chapters for this. Internal, just to help me keep it straight, that it's not, and I should put this is a capital letter U, so it's got the footies on the letter. Capital U, internal. The energy content of a gas is related to its temperature only. This is very, very, very cool. Okay. I'm gonna stop the segment there, and then we'll pick up here with some consequences of that.